Hello, and welcome to this podcast from Princeton University Press. My name is George Miller, and my guest today is Timothy Gowers, the editor of the Princeton Companion to Mathematics. Tim is Rouse Ball Professor of Mathematics at Cambridge University and a former recipient of the Fields Medal, awarded to those who have made an outstanding contribution to the field of mathematics and widely regarded as a Nobel Prize of the maths world. The Princeton Companion is impressive not only for its substantial size, but also for its inclusiveness, its range, and its approachability. When I met Tim in Cambridge, I wanted to know what had attracted him to such a monumental project in the first place.
Well, it was one of those things, if I'd known how much time and effort it was going to take, I might have thought a little bit harder before saying yes. So I kind of got sucked into it in a sense. The first thing that happened was that David Ireland, who used to work for PUP, came and visited me without saying exactly why, and he and I had lunch together, and he started talking about his idea for a book along these lines. It was close enough to ideas that I had had in the past of sort of, wouldn't it be nice if there were a book of such and such a kind type ideas, that when the moment came that he said, but I'm actually going to ask you whether you're interested in being the editor, although I didn't absolutely agree on the spot, I basically knew that I was going to agree, and a few weeks later I formally agreed to do it. But then the amount of work that's gone into it has actually been because of the particular way that I've gone about editing it, or I and my co-editors, I should say. We decided that a book of this kind, which is aiming to present mathematics in a very accessible sort of way, that if articles came in that didn't seem to be as accessible as they could be, then rather than just accepting whatever we got, that we should make a big effort to make them more accessible. So there's been a huge amount of rewriting. Some articles have come in and been absolutely fantastic from the word go, but those are a small minority, and most of them have been not exactly what I was looking for. They've had a lot of extremely good aspects to them, but Princeton Companion is a little bit different from a typical mathematics survey article, and it was hard to explain in a sense what exactly it was we were aiming for, and in the end the quickest way of getting to what we were aiming for, or getting closer to the sort of ideal that I had in the back of my mind, was simply to do a lot of rewriting in consultation with the authors, and the authors have responded marvellously to that, and sometimes I've said, could you do something, and they've put in a lot of extra work after submitting their first drafts, and sometimes I've directly rewritten things, and they have then said, I like that bit and I don't like that bit.
And in your preface, you make clear that it isn't an encyclopedia, it's a companion, and I wondered if you could say a little bit about what the characteristics of it are as a companion as opposed to an encyclopedia.
I would say the main difference is that an encyclopedia, the articles, although there are links between them, they're sort of more isolated. An encyclopedia is a collection of articles. It's organized alphabetically. You'd never think of, you would not normally think of reading an encyclopedia starting at page 1 and going to page n. It would be treated purely as a reference book. Whereas here, we've tried to organize the book in a way that there's more of a progression through the book. It's organized not alphabetically, but thematically, and the idea is that I don't expect people to read it from starting at page 1 either, but if they did, they would find that the articles were organized in such a way that the first part of the book, for example, is preliminary discussions in some generality about what mathematics is, and then the second part is something about the history of mathematics and how some of the broad themes of modern mathematics came into being, and so on. And you just progress through the book, and each bit of the book, it makes some sense to have familiarized yourself with earlier parts. And I think that should give it a very different feel from an encyclopedia. Another important difference is that we're not encyclopedic in the sense of being comprehensive. We don't regard it as a necessity to cover every single important mathematical topic, because there were only 1,000 pages or so to play with, and that would be impossible. You'd need far more than that. So instead we try to produce a representative sample of important mathematical topics, so that you really present what mathematics is like globally, but it's not necessarily a book that you could guarantee to find the answer to a question. If you said, I wonder what such and such is, you might not find it in the book. So the way one would use the book is a little bit different, I think. I think it'd be much more likely that you'd browse in it than just use it occasionally to look things up.
How does the companion compare to online resources in the field of mathematics?
Well, that's a good question, because in some ways it's quite similar. In some ways you've got accounts of lots of different concepts in mathematics, as you have, say, on Wikipedia. And it's got cross-references that feel a little bit like links from one Wikipedia article to another. The differences between this and Wikipedia, there are various differences. One is that on Wikipedia and other sites, there are much longer articles in the book, as well as the shorter ones. And these articles that describe whole branches of mathematics, setting out in careful essays, are not a feature of Wikipedia. Another is that the whole way that the book has been edited is very different. It has its advantages and disadvantages. And one of the disadvantages, I suppose, that the book has over Wikipedia is that it doesn't cover nearly so many topics. But an advantage is that it's been very carefully edited to be as accessible as possible. And all that work that's gone into all of the articles, I think, will pay dividends. And so I hope that the two resources will just be complementary. You'll have the Princeton Companion that will be very good for some things, and Wikipedia that will be very good for others. One other difference is that the fact that the book is organised in the way it is, as I was talking about earlier, that you could sort of in principle read the book from start to finish, that gives it a very different structure. It's got a sort of linear structure, and Wikipedia's got a more sort of tree-like structure, which is good for some things. It's good if you just quickly want to look up one topic. Less good, I think, if you want to get a feel for the whole of mathematics. So as I say, I think the two are complementary. And
presumably another difference is that your team of contributors was handpicked from among the world's most eminent mathematicians.
Well, that's true too, yes. I think that does show in many places.
And it seemed to me, looking at it, that its purpose was not simply to describe the current state of mathematical research, but there was also a subtle but discernible sense in which it was advocating mathematics, or it was arguing for mathematics both to those who were not already inside the discipline, and also, in a sense, trying to make connections for those who were in the discipline but perhaps weren't aware of all the branches of their subject.
Yes, that's true. I mean, well, I could say two things in response to that. One is that one of the instructions that I gave to authors was that I wasn't just interested, say that they were writing a short article on a certain mathematical concept. I didn't want just to know the answer to what is X, but I also wanted to know the answer to the question, why X? In other words, what is the justification for being interested in X? So that was an important aspect of the book. The second thing to say is that I had thought a long time ago it would be very nice if there were essays about other branches of mathematics, so that I could read, rather than talking to somebody, I could actually just go and read an account of why some other area is interesting, what its priorities are, what the main results in the area, what sort of techniques are used, just to get a feel for what other people are doing. Because if you don't make some effort to do that, you can really just know, and this has been the case of me and before working on this book really, that I knew about my corner of mathematics and had almost no idea what other people were doing. And now, as a result of carefully reading lots of articles in the book, I have a far more filled out picture of mathematics as a whole, and I hope that other people will be able to get that.
And part of presenting the human face, if you like, of mathematics is that you have entries on mathematicians of the past. And I wondered how you arrived at your list of mathematicians for inclusion.
Initially, we had planned to have mathematicians right up to the present day. The idea was, in each case, that it was not going to be just a potted biography, but we wanted to explain in each of these articles why the particular mathematician was famous and worth worrying about today. And there'd be just a little bit of biographical information as well. But perhaps, predictably, we eventually decided that choosing some selection of 30 or 40 present-day mathematicians was just going to be too difficult a task. Where would you draw the line? So we abandoned that idea and we decided to have a cut-off of about 1950, and by that I mean a cut-off of when the interesting work by that particular person was principally done. I found after that, though, a lot of the list just wrote itself. I mean, I just, off the top of my head, I wrote down a list of all the famous mathematicians I could think of and showed it to other people, and other people said, you've missed out, blah, 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 and gradually it built up. And we now have, I've forgotten, I think around 100 entries.
One of the interesting things to me as a non-mathematician was getting a glimpse of how mathematicians actually work and how they circumscribe a problem and work on a problem. I presume that is there partly as an encouragement to those who may be considering going into mathematics in a serious way.
That idea of advice to a young mathematician I had because on the rare occasions that I have read articles or little accounts by mathematicians senior to me about how they go about doing mathematics, how they choose problems to work on and how their careers progressed and so on, I've always found it incredibly illuminating, and so I just thought if I asked a few people to do that, it would be an almost guaranteed, highly readable, highly interesting article, and indeed I would say it's turned out that way. I've been very, very pleased with the entries. I think it's one of those things that, again, it's quite easy not to communicate. There are certain aspects of mathematics that are very important, or the mathematics as a practice, that everybody just picks up on their own, and they're not usually communicated. And it's actually not that hard to communicate them, but they just aren't the natural, you couldn't write something in a maths journal about how you go about research. So it's the kind of thing that would normally just happen in conversations and so on. But not everybody is lucky enough to be in a position to have a conversation with Alan Kahn or something.
I was amused and interested to see that the advice included such things as having walks to think about problems and turn them over, and allowing yourself time to sit in a darkened room and not to cut yourself off from your fellow mathematicians.
Yes, all those things. One of the nice things about this particular section was that I was a little bit worried that if I asked more than about 3 people, then people would all start saying the same thing. But extraordinarily, there wasn't much overlap at all, and yet everything that people said seemed to be interesting and worth saying. Yes, one person said that they had a hard job convincing their spouse that a lot of their best work was done while lying on a sofa.
And in the section where you look at maths intersection with other subjects, you don't just include the obvious candidates like chemistry and statistics and so on, but you also take it as far as music and indeed beyond to the plastic arts.
Yes, that was another thing that we wanted to do. We wanted to have, well, the section is called The Influence of Mathematics, and there seem to be 2 rather distinct sorts of influence. And in fact, originally we were going to have 2 sections, but then we merged them. And one was more intellectual influence, using mathematics in something like economics. And another was a more practical use, such as in finance or something like that. And of course, the influence that mathematics has had on different areas is very different. So the influence it's had in, say, image processing is quite pure and seriously mathematical, whereas the influence that mathematics has had on music, you could question how important that's been. But it's clear that a lot of people in the musical world are very interested in mathematics, but the nature of that article is rather different. Whereas in something like image processing, you might use a pretty serious theorem of mathematical analysis in order to develop an algorithm for dealing with images that you might see on your computer. The sort of mathematics you use for music is likely to be more elementary, a little bit of group theory and that sort of thing. But nevertheless, it seems that the spirit of mathematics has been quite influential in that area, and also on some artists, painters and sculptors. I get the impression from that article that a lot of artists towards the beginning of the 20th century who were very interested in mathematics were not really interested in the sort of mathematics that's mostly discussed in the Princeton Companion. They wouldn't be interested in algebraic geometry or something. But they were nevertheless sort of inspired by the fact that mathematics existed and what they understood of relativity, which is probably not the same as what a mathematician would understand of relativity, but nevertheless seems to have had an indirect influence on them.
And drawing right back to take the wide-angle view of the book, where would you say it sits on the applied versus pure axis? Because some of the core of it seems very pure, and then there are other quite real-world applicable sections of it.
The book as a whole is principally a book about pure mathematics. Of course, there is applied mathematics in it, because a proper appreciation of pure mathematics does require you to have some understanding of applied mathematics. I mean, a lot of the reason that pure mathematicians in some areas work on the problems they work on is that those problems originated in physics and applied mathematics, and that's what gives them what gives the sort of general field its impetus, or sometimes its initial impetus, sometimes a field can take off from that and become interesting also for pure mathematical reasons. So I'd say the main priority of the book is pure, and also in the section on applications, sort of just straight applications to other areas, of course, that's another way of justifying it, in showing that the pure mathematics has had uses outside itself. So uses both at the beginning to get the area going and at the end to apply it. And that gives some justification to the pure mathematics. But nevertheless, the central focus of the book is to explain and justify pure mathematics.
What kind of sense would a reader get of the hottest topics, if one can put it as crudely as that, in mathematics today?
I think you can pick it up through reading the book. We haven't explicitly tried to say these are the most interesting things and those are less interesting. I don't want to make those sorts of judgments. But the fact that, actually I can tell this quite easily from a proof that I have of the book on my computer. I can type in something like Fermat's last theorem and I'll get a lot of mentions of it, because a lot of people from different areas are interested in it. It sometimes gets mentioned in articles about something quite different because a technique that's used in such and such an article was also used for Fermat's last theorem or something like that. So some of the big problems that have been solved, that and another obvious example is the Poincare conjecture, they get mentioned a lot because understandably people are very interested in them. And some mathematical tools get mentioned a lot, and you just get a sense with that of some of the things that are hot.
For you personally, were there areas which you were discovering for the first time, or new excitements that you had as a result of editing this book?
Well, there are lots of different areas that some of them I used not to be interested in out of sheer prejudice, really. Something like numerical analysis. It has a reputation amongst many mathematicians for being a dull subject, but I don't think you can read the Princeton Companion article on numerical analysis and continue to think of it as a dull subject. When you read that, you realise that the reason you think it's dull is because you think that numerical analysts are just interested in errors that creep in when you write a program on a computer, and it turns out there's much more to it, and that's not the main thing that numerical analysts are interested in. I just didn't know that until I read this article. Other areas I was not exactly uninterested in, but I just thought that they were so difficult that I didn't really have any chance of ever understanding, even in broad terms, what they were. And an example of that is an area called arithmetic geometry. There's a beautiful article on that subject that really it explains in a very elementary way. It sort of guides you into the beginnings of that area and then tells you a bit about what's going on in current research. As a result of which, something like the Birch-Swinnerton-Dyer conjecture, which I had thought of as something I wouldn't really appreciate, I don't begin to understand the work still that has gone into that, because that is very difficult and advanced. But at least I understand the conjecture enough to think, gosh, that's extremely interesting. I wonder what the answer is. And so I didn't quite have that feeling before. I just knew that it was a famous conjecture that a lot of people were interested in, and now I have had my interest in it somehow piqued by what I've read in the book.
And would it be fair to say that if in 10 years' time there is a new cohort of graduate students who look back and say the Princeton Companion was one of the things which set them on a course of serious mathematical research, that your job will have been a satisfying one? Very
much so, yes. My hope, and actually belief, I'm quite confident about this, is that it really will fill a niche that needs filling, and that a lot of people will find that it really helps them to, not to learn areas of mathematics, but to do a sort of preliminary scouting of an area and get to know what it is that's out there to learn. So it will help people at the very outset of their career maybe choose a research area. I think if they say, I've been quite interested as an undergraduate in functional analysis, but what's research in functional analysis like? And they could go and have a look at an article on operator algebras and maybe get some idea of whether that's the kind of thing for them. So that, and also improving communication between areas and enabling also people doing their research. They might, if they've read the Princeton Companion, they might just know what's out there, so that if there's some problem they work on that could actually possibly be solved with the help of tools from another area, they will at least know that that area exists and what sorts of tools are available. And so I hope that it'll be very useful in that sort of way.
I was talking to Timothy Gowers, whose Princeton Companion to Mathematics is available now. Thank you for listening to this podcast from Princeton University Press.